Estamos transmitindo.
Bom dia a todos e todas. Nós estamos aqui para iniciar as atividades do quarto workshop em Data Science. Esse workshop está sendo realizado pelo Departamento de Estatística da Universidade Federal de Lavras. Sejam todos muito bem-vindos. Nesse evento nós teremos 8 palestras, 2 tutoriais, uma mesa redonda, 2 minicursos e ainda 2 sessões de comunicação oral. Então, serão 3 dias, muitas atividades interessantes aí, foram pensadas para vocês. E nós esperamos, a comissão organizadora, espero que todos aproveitem bem esse evento. Então, a gente vai dar início às atividades agora. Eu estou aqui com meus colegas, Geraldo e o Júlio, do Departamento de Estatística. O professor Júlio vai conduzir a palestra de abertura. Então, vamos começar, Júlio. A primeira palestra.
So, Minnie, first I will just give some Portuguese words to my likely audience, and then I'll shift back. So, Professor Minnie Chetinkaya Randall is é uma professora, né, da Universidade de Duke, e ela está tanto no departamento de estatística, no programa de graduação em estatística, quanto no programa de Computational Media, Arts and Cultures, que é um programa voltado para educação midiática, né? E o trabalho dela é principalmente em educação em estatística, pedagogia da análise de dados, ênfase na computação, pesquisa reproduzível, ensino baseado nos estudantes, né, que é uma das coisas que nós discutimos bastante durante o nosso workshop, e educação aberta. Ela trabalha com R, POSIT, e, na verdade, pelos que sugere a palestra dela, ela trabalha na metodologia que aparece para desenvolver pesquisa nova. Então, just switching back, Minnie, I would like to thank you very much already for the talk you give us and for sharing your knowledge in this very important subject for us. So, please go ahead. I will try to translate when we have some Portuguese questions or something, and I'll try to send the feedback. O som agora não está legal dela, Geraldo.
Eu acho que ela desligou.
Minnie, your sound.
Can you hear me now?
Yeah.
Okay, wonderful. All right. Thank you very much for having me this morning. So I want to talk about a project that I've been sort of working on, continually have been working on over the past few years, and do so in the context of teaching a semester-long data science course. So if you're familiar with the R for Data Science book, you've probably seen this diagram before of the data science sort of Krebs cycle in a way. And so this diagram was the inspiration sort of for the design of the semester-long data science course that I've been teaching over the years at Duke University. And then I was at the University of Edinburgh for 2 years in between, and back at Duke now. And I've taught this course there as well. And bits and pieces of it I've taught as workshops and whatnot, and a variety of other people around the world are teaching out of this curriculum. And this is what the curriculum looks like. So we start with a week of Hello World, where we introduce students to the toolkit of the course. And then 3 major learning units throughout the course. The first one is exploring data, where in order we go from visualizing data, then taking a step back and saying, well, what if the data isn't ready to be visualized? So wrangling data, and then taking one more step back and saying, what if the data isn't even there? So importing data. And then we have this unit takes somewhere around 5 to 6 weeks. And then we have a week on data science ethics, where we touch on things like misrepresentation, data privacy, and algorithmic bias. During this week, things are not very code heavy, unlike the first learning module. And it also is an opportunity for students to start thinking about their semester-long projects and write proposals for those as well. And then we dive into another lengthier and code-heavy unit called Making Rigorous Conclusions, where we bring in some statistical ideas as well. We start by modeling, particularly predictive modeling, and then touch a little bit on inference from the simulation perspective. And then finally, we end, depending on how many weeks are left in the semester, with a unit on looking further. This is usually where the instructor, myself, or whoever is teaching this course brings in things that are of interest to them or that the class has said is of interest to them. So generally during this unit, I'll bring in topics like making interactive web applications with Shiny, or text analysis, or Bayesian inference, or something like that. Something we're not going to get to dive into a lot in the class, but something that perhaps makes the students go, oh, I want to take another course in data science or statistics. And you can see throughout this whole diagram, there's this idea of communicate running through. Every single thing the students do in the course is done in a reproducible computational document using Quarto, every single assignment, every single in-class exercise. So that is part of the communicate aspect, where they are creating things, artifacts that are fully reproducible. And we also talk about how to communicate their data science findings to different types of audiences that have experience with data science, or audiences that don't have experience with data science. So that's a sort of a thread that runs through the whole course. So what we're going to do today for a few minutes is act as if you are actually in the class, so I can introduce you to what happens on the first day of class. So welcome to the first day of class. And this is what the first day of class goes like. We come to class, I introduce myself, I try to take no more than 5 minutes doing that. And then we say, okay, let's get to working. Before we even talk about the syllabus and stuff, which are important things to do that we'll still get to during that first class. But before we get there, we say, let's go to Posit Cloud or similar, depending on the institution where I've taught. The access to compute that I've used has changed, but what hasn't changed is the fact that students aren't installing anything. They are going to their browser, to a server-based solution to access R and RStudio. So let's give the example of Posit Cloud here, and then we give them an project that has already been prepared by me. One of the examples I love using on the first day of class is based on this data set called UN votes. And they open this project. There's already a Quarto document there for them, as well as a compute environment that has all the R packages that they might need installed. So we ask them to open the Quarto document, and we ask them to render this document. Once they render the document, they get to see this visualization. So in this visualization, in the original version of the visualization, they are seeing the same diagram with sort of 3 countries: Turkey, United Kingdom, and United States. And these are the percentages of yes votes in the UN General Assembly on a variety of issues. Colonialism, arms control and disarmament, nuclear weapons, so on and so forth. And then what we say is, before we teach you any code, go to the code in the document and change something so that you can take this figure and change it to, something else. Let me go back real quick. Change the country Turkey to something else of interest. So how are they able to do this without me teaching them any code? Well, even though they don't know how to write R code from scratch, they generally can. Read through the text, because all of the code is documented in the Quarto document. Sort of zero in on where it says Turkey in the code, and then change that to another country, say France, and then re-render the document and recreate a new version of this visualization. So within the first 15 minutes of the course, they have created a visualization, and we ask them to talk to their neighbor about what country they chose, whether they are, surprised or not by the results they're seeing in terms of how these countries are voting, and also talk to their neighbor about why did they choose that country to begin with, so that it can be sort of an icebreaker as well. And importantly, another thing we mention here is that we don't have the full story here. We don't know what a yes vote means. Does a yes vote mean yes to colonialism, or does a yes vote mean, yes, we should not be supporting colonialism? So these are also things that we touch on here, that we talk about how these are not things that we are going to solve by writing more code, but we will solve by diving deeper into the data and understanding what the data actually shows us and what the data is about. Then we get back to the rest of the class. There's the rest of the day one is about introducing sort of the logistics and the assessments and whatnot of class, but students leave day one having created a visualization and having modified a visualization, and even having written some code on the first day of class, because they basically, were able to change this one country to another. So let's take a look at the rest of the semester. We're going to talk about three things today: content, pedagogy, and tooling. So let's start with content here, and we're going to do that in three examples. The first example is the Fisheries of the World example, which is based on this somewhat horrendous visualization. The data visualization folks at Duke were provided as part of a consulting project, I think, which uses data from Wikipedia on sort of the fishing amount of each country, so whether that's capture or aquaculture, so farm fishing. And then these visualizations were created, you can probably guess, with Excel, but we show these visualizations to students and ask them, like, what is going on here? Sometimes they will say things like, we have a right skewed distribution, for example, but then if you pay attention to the x-axis, that is not what that is. We don't have numbers on the x-axis here, we have countries. So these are sort of nonsensical visualizations that are not very useful about understanding how fishing happens around the world. So first, what we ask students to do is use this example to teach join. So in this case, we say, well, we have this data set with countries in it, but let's find another data set with continents in it as well and join these two data sets. And then when you try to work with any data set that includes country names, you've probably run into this issue where things don't match 100% to another data set. Sometimes this is based on spelling differences, and sometimes it's because of political reasons, like whether a country's name has changed or whether a country is recognized as a country by another country that has put together the data set or not. And here you can see all three of those when we look at countries like the Democratic Republic of Congo, Hong Kong, or Myanmar. So we say we are going to have to make a decision about how we handle these countries. And in this case, we had made the decision that we're going to look at their geographic positioning and place them in continents accordingly, not, getting into conversations around whether we recognize a certain entity as a country or not. But this brings together into this, simple example on data joins, discussion on data science ethics as well, because we are ultimately making some decisions about some countries. And then we critique the original visualization and improve that. So here is one way we can improve that visualization by plotting instead the average share of aquaculture by continent, based on this new join data set that we have put together. And you can see we're using ggplot to sort of create our improved visualization. This also becomes a great opportunity to talk a little bit about mapping. In this case, we've drawn a choropleth map of the same data, this time at the country level as opposed to the continent level. And those gray areas represent data, countries for which we don't have data, And we sort of get a chance to talk about both the nitty-gritty of creating one of these plots, but also the fact that when you create one of these plots and have missing rates at this level, how it is, not very informative. And here's an example of a student project. So this is actually a team project that was clearly took the inspiration from this example that we did, the fisheries example that we did, particularly the choropleth maps. So at the end of the semester, the students in their project, their semester-long project, wanted to look at regional differences in average GPA and SAT. So this team chose this question of wanting to explore regional differences in the GPA and SAT score across the US and the factors that could potentially explain them, and made these visualizations. So what's nice to see here is that they were able to take that one example and apply what they learned to a completely new data set. The second example I am going to give is going to be based on web scraping. And this is an example I happened to develop while I was in teaching at the University of Edinburgh, and that timing happened to coincide squarely with sort of the height of COVID. And there are two reasons why I want to go through this example as an inspiration for you. One is that I think it's a neat example on web scraping, but also doing more things with the data that you have scraped. And number two is it's an example of taking a curriculum developed elsewhere. This curriculum was originally developed in the US, and then sort of localizing it for yourself so that you can use examples that might be more interesting for your students. So during the height of COVID, the First Minister of Scotland at the time, Nicola Sturgeon, gave a COVID briefing every single day at 12:30 p.m. And I was sort of obsessed. I think the whole country was obsessed with sort of listening to these briefings to get a sense of what was going on with COVID. And I realized that the Scottish government actually posted the text of this on their homepage, on their sort of governmental page. So we took a look at these sort of COVID briefings. And if you click on each one of these, you'll see sort of the same structure, a title, some metadata about it, and then the text of the briefing itself. So we took one of these pages and we use that to teach web scraping. So using a tool like Selector Gadget, we've been able to select these different sort of areas on this web page and grab the text. Soon as you start talking about grabbing text off a website, you need to introduce ideas about text parsing. You can see there's different types of data here, particularly the date column requires that we start introducing ideas around different data types. And then also, whenever you are working with text data, you can't avoid working with regular expressions as well. So this becomes an opportunity to introduce regular expressions too. Then we said, okay, we were able to scrape this one single page, but she's giving these briefings every single day. And if we want to analyze these data, really what we need is an opportunity to sort of leverage the code we wrote for grabbing the text from one page and then apply it to all of these pages where every single briefing exists. And so we then say, well, we wrote some code to create, to scrape this one page. Let's write a function that wraps that up, and then introduce ideas of iteration to map that function across each one of these URLs so that we can create a data frame where each row of our data set is one of the COVID briefings, and we have columns that correspond to different fields like the date, location, so on and so forth of the briefing. And then once we have the data in hand, we go back and we can say, okay, we now have the data. We've already learned previously in the course how to visualize and wrangle these data. So some of the things the students that semester wanted to look at were things like, well, has the text been getting longer as COVID continued, and she continued to have to give these speeches. So that's the first visualization you can see here, maybe a little bit. And then also another thing that happened in Scotland, and I think around the world as well, is that government, countries used to talk about social distancing, and then they realized how that was sort of a alienating concept where people were feeling alone. And then it came to the Scottish government at least made a decision to refer to that as physical distancing. So in the visualization at the bottom, you can see how early on in COVID, the First Minister generally referred to social distancing, and then later on that came to be physical distancing. And we were able to create this visualization by parsing the text and looking for words like social distance or physical distance across time. And finally, later on in the course, in that looking further unit that I mentioned at the beginning of the talk, we go back to this data and we did a module on sort of text modeling. It's not part of the course curriculum. It's not something that the students get assessed on, but it is something that we are able to sort of introduce to them in a lesson to say, hey, if you keep learning about data science, this might be the sort of thing that you can do. And here we then, what I did sort of separately was to scrape the data for the UK speeches. So these were the speeches given by Boris Johnson at 10 Downing Street. And so we scraped the text for these as well. And then we took a look to see how these texts were similar or different. So calculated some text frequency, inverse document frequency measures for them. And one of the funny things that we realized is that they said the word slide a lot in the UK speeches. You can see that on top, but not in the Scottish speeches. And that was just because someone kept saying, next slide, please. But then also there were other differences in terms of the content. Like they used things like, we're going to defeat this disease a lot, versus the Scottish speeches were much more scientific in a way, focusing on numbers and sort of what was happening, as opposed to sort of having these emotional sort of undertones to them. So this was a fun example in saying, hey, you've learned how to do something, and if you continue to learn more, you can do even more with the data that you have scraped. And another thing that we were able to bring into this unit is data science ethics. So before we could scrape all of these data, we have to ask two questions. Can we, as in, are we legally allowed to scrape these data? And for that, you can inspect the robots.txt file of a website. So we get to talk about the technical details of that and see if we're allowed to scrape data from it. And then secondly, we are able to talk about, should we scrape these data? Are there ethical implications of scraping these data or not? So that became a nice venue for talking about those two. And here's an example of a project that the students did based on what they learned on this unit. So here they were again looking at SAT and ACT scores to predict rankings on this website that I actually did not know about, but they all seem to, called Niche College Ranking List. And so you can see the website here on the left, where you can see a little box for each of the colleges. And then what the students did were to click on each of those sort of college names, go to a page just like the briefings page, write some code to scrape data from that, functionalize that code, and then iterate it over each of the colleges to create these visualizations and fit some models to them. And the third and final example I'll give is actually a pretty sort of standard example for introducing logistic regression, building a spam filter. So we start with sort of the obvious of take a variable that might be some data about an emails. So based on an email corpus, we looked at the number of characters in an email to indicate, how long the email is, and use that to predict spam. So we introduced the idea of logistic regression and prediction, but note that this course isn't meant to teach all of modeling to students. It's sort of meant to give a taste to students in terms of like what there is to learn in the world of modeling. And then so we quickly move on to talking about in this unit the idea of making a decision with data. So things like decision errors, the notions of sensitivity and specificity, and also building some intuition around loss functions. Talking about things like, how do I feel about some of my emails accidentally going to spam when they shouldn't, versus how might you feel about that? And this idea of different people might have different loss functions. We don't actually end up introducing things like L1, L2, L3 loss functions in this course. That's well beyond the sort of the modeling curriculum of this course, but the goal is to build enough intuition so that when they go to their second course in statistics, which is at Duke at least is based on is a regression course, they are prepared to sort of consume those ideas. And here's an example of a project that another team of students worked on. I was not familiar with the game League of Legends, but turns out this team, quite a few of the students played this game. They actually first scraped some data from, the League of Legends forum or something like that. And then they used the ideas of logistic regression to sort of answer this question that is sort of important within the context of the game of whether a gold lead or an experienced lead was a better predictor of which team wins the game. One of the nice things about this example is that they really were able to bring in something that is of like personal interest to them. And in fact, in this particular team, one of the students was a big fan of this game. And so this student really took the lead in explaining the context to their peers. And then they were able to analyze these data and create this presentation based on what they learned in the class. And here's another example of sort of where the analysis didn't pan out so much, but still was sort of wonderful to see how students put their sort of what they learned into use. So this team was looking at critiquing Hollywood relationship stereotypes and looking at whether the average age difference between two actors in an on-screen relationship changed over the years, and whether on-screen same-sex relationships have a different average age gap than on-screen heterosexual relationships. And one of the things they realized is that there were barely any there were barely any same-sex relationships on screen prior to late 1990s. And this was not something the students who are much younger today expected to find. So sort of the question that they posed did not really pan out with the data they were able to scrape and decide to model, but this was still a learning experience for them in terms of, having a hypothesis, collect some data on it, and then finding out that sort of the question you posed is not well suited to be able to be answered with these data. All right, so we talked a lot about content, so let's make a few remarks about pedagogy. I won't go through the pedagogy of the entire semester here, but I want to talk about a few things. One of the sort of the most important features of this course is the aspect of live coding. So students learn about many data science sort of concepts and learn to actually implement them with code in R using primarily tidyverse-based tools. So every lecture, along with time for students to attempt exercises on their own, there's a live coding component where the instructor is in front of the classroom and instead of running through slides is actually writing code and walking the students through these examples that I gave you. The 3 examples are all implemented with live coding in the classroom. Students work in teams. They work in teams for the weekly lab sections where they do computational labs. They do periodic team evaluations so that they get some feedback from each other about how they're doing and how they're contributing to the team. And then there's this term project that goes, that spans basically about 2/3 of the class, not the entire semester, but about 2/3 of the class where they're working on in their teams. And this is an iterative project that they work on many milestones along with their teams. We have weekly quizzes that the students take online. These quizzes are created with the LearnR package, so they write some code and then they answer some questions with that. The goal of the quizzes isn't really to sort of test them constantly. They're worth very little in terms of number of points in the class. However, each of these quizzes end with a brief reflection of the week's material. So we give them an open-ended space and ask them, what are some concepts that you learned that you're struggling with, or what was difficult in this quiz? And we ask them to write for a minute. This idea of a minute paper is something that our colleagues in the humanities use a lot. So I borrowed that here to, give the students an opportunity to reflect. And then what I do is I either read through those reflections, or if the class is very large, I've taught this course with up to about 300 students in it, I'll do some text analysis on it, count some words, count some bigrams, and take a look to see what are some concepts that emerge as being mentioned to be challenging for students. So we start the next week's lesson based on what the students have reflected on. They also do peer feedback, particularly as part of the project. We will open sort of the repositories of a team to another team to go in, reproduce their work, and leave feedback for them. And what's nice about this sort of peer feedback is the good things tend to be contagious. People don't tend to see sort of something bad in a peer's work and, sort of take that with them, and then the bad doesn't tend to spread. But if there's good practices that one team is doing, this usually helps that spread. They learn from each other, and they also tend to give very constructive feedback to each other. And usually we don't grade the students based on student feedback. So it's not like they're losing points based on the peers' comments, but they can use them to make their work better before they actually get graded on it by the course staff. And the last bit of example I'll give as part of the pedagogical toolkit of the course is creativity. I think that assignments that make room for creativity is a great way for allowing students to sort of bring in themselves into the classroom and hopefully get motivated to learn more. So how can we do that? One way is, with a semester-long project. The project description basically says TLDR, so too long didn't read, ask a question you're curious about and answer it with a data set of your choice. This is your project in a nutshell. Everything else in this lengthy project assignment is to help students guide students through this and also give them some information about how they're going to be graded. But really, we're telling them, do something with what you learned in the class, so they get to be creative. And you've seen some examples of the project work and like how varied it can be. However, I acknowledge that this type of assignment can be quite difficult to implement if you have a very large course and if you don't have a lot of support in terms of student, TA support, for example, for both supporting your students throughout the project, but also for grading the work that they turn in. So if that's not feasible, another approach is to do something. I should also mention this. So we have a paper on implementing sort of the data science projects in the classroom. So I will share the link to these slides at the end if you're interested in the paper. This paper was with my colleagues Mina Doju and Wendy Rummerfeld, 5 W's and 1 H of term projects in the introductory data science classroom. And we give very sort of directed guidance into create one of these. But here's another example that's a lot more low-key than a semester-long project, which is make a plot ugly. So that's basically what the assignment is. This is a lot easier to grade, requires a lot less student support, but still gives an opportunity for students to bring sort of something their own to the classroom. And so we give them a very simple plot and say, just make this as ugly as possible. So here are some examples from student work. And note that these are students who I haven't taught them how to change these features of a ggplot. One of them wanted to make it look like I think it was a rugby field or something like that. The other one just wanted to make it as ugly as possible in terms of the color choices. But the important thing here basically is that they learned the nitty-gritty of ggplot2 themselves and got really motivated to sort of get the ugliest plot possible. And at the end of the semester, we usually have students vote on the ugliest plot and give them like a mini prize or something like that. So it brings an element of fun into the classroom as well. And finally, let's talk a little bit about the tooling. So how does the tooling work in terms of the students and also in the back end in terms of the instructor? The student-facing tooling is actually very minimal, or let's just say minimal seeming, and I think that's the beauty of it all. Students access the R environment where they work with RStudio as their IDE in the browser. The goal is to make it as quick to get started with coding as it is to get started watching something on Netflix. So across different semesters, I've used either Posit Cloud or another browser server-based solution. For example, at Duke, we have our own in-house solution for RStudio servers, but students just go to their browser and log in, and they're in an RStudio session with all the packages they might need loaded. And in addition, they use Git and GitHub. Well, really, on the back end, though, in order to facilitate this, the instructor-facing tooling is, a lot more extensive. So the instructor uses these tools, RStudio and Git and GitHub as well, but also we have an R package called GH class that we use to create student repositories and manage all of their work on GitHub. We use GitHub Actions and another R package called Checklist to run automated checks on student work. And we use a suite of packages called LearnR, LearnR Hash, and Grade This to create those weekly quizzes, collect data from them from students, and then sort of give them constructive feedback as they're working on the quiz as well. And really, on the student-facing side, obviously, it is not just R, right? They're in RStudio, they're creating documents in Corto, they use a bunch of packages from Tidyverse and Tidy Models, they have to learn what Git is, and many other packages get introduced along the way, but students don't have to individually install these things one by one. They work in an environment where everything sort of works for them so they can focus on the data analysis and not sort of the creating the infrastructure aspect of things. And I should note here that this is not because I don't believe installation is not an important learning outcome. I think that it just is something that can be put off a little bit for the benefit of being able to dive into data as quickly as possible. Yes, within a 4-year undergraduate curriculum, if a student is saying that they learned how to use R, they probably should have installed R once on their computer as well. But I don't think that's something that we need to bog down students with on the very first day of class. Instead, we can use that exciting moment to get them to do something exciting, like create a data visualization. So a little bit about how we use Git and GitHub in the classroom. So we have a course organization on GitHub, which is a sort of a concept that GitHub makes available. And within this organization, we have students as members, and every single assignment of a student is an individual private repository that the course team has access to, but students don't have access to each other's. So if you have, 3 students in your class and 4 assignments, you end up with 12 repositories. You can imagine if you have 100 students and 10 assignments, you end up with 1,000 repositories. So the number of repositories are huge, but we can create them programmatically using the GH class package. So it's not like the instructor is clicking on a bunch of buttons to make that happen. And ultimately, it doesn't matter how many repositories there are, because for each student, all they see is their 10 or so repositories. Each repository then maps onto an RStudio project. So at the beginning of each assignment, the student goes to GitHub, to the course organization, grabs the URL of the repository that was created for them with some starter materials and all the data sets that they might need, and clones that as an RStudio project. There are also the concept of teams, as we said. So this is for the projects. So we create one repo per project, and we create teams of students within the course and give access to that team to their repository only for the duration of the project. So this is where we then introduce ideas of, working collaboratively on GitHub. What is a merge conflict? How do we resolve them? And as I said, this project starts later on in the course. So they're not necessarily being, they're not sort of challenged by things like merge conflicts on day one of the class. We introduce that a little bit later, once they've gotten a chance to work on things and understand the Git workflow individually, when there was no sort of concern around merge conflicts. And then throughout the project, at certain moments, we open certain teams' repositories to other teams. So the peer review process actually leverages, real data science workflows of doing code review. So project A gets access to project B's repository, but only read access, so they can't change anything there. I place an issue template in this repository where I have questions like the ones you can see on this slide here, where we give them some directed guidance for, reviewing this project. And so team A ends up reviewing team B's project, leaves an issue, and then at the end of this peer review phase, we take away team A's access to team B's repository so team B can continue to work on their work. All right, and here's an example of one of the projects from the class. You can see that at the end, they create, their project is actually a single Corto document. We asked them to turn off the code. So we said echo equals to false. Let me scroll through that one more time. And so they have a write-up and some sort of tables and visualizations. And you can also see on the top bar of this, that there's a URL associated with this project. So each team creates, has a repository in which there's a Corto document where they write up their project. And then what I do on the back end is push one more file into that repository, a Corto YAML file, which then changes that repository to a Corto project or a Corto website. And at the end of the semester, should the team members want to make their project public, we give them an opportunity to do so after the grading is done and everyone has agreed to making their work public, and they end up with a persistent URL for their project that they can put on their resume. So it's sort of a souvenir they can take with them at the end of the semester and say, this is what I worked on in class. And then there's a GitHub repository that we make public at that time as well. And they can say, and here is my repository where I did this work. So if you are thinking about implementing version control sort of as a learning objective in your course, another paper that I would direct you to is this paper we published back in 2021 in the Journal of Stats and Data Science Education on implementing version control with Git and GitHub. And this paper was sort of written by, with a bunch of colleagues here, and each one of us gave our perspective on how we use Git and GitHub in the various courses that we teach. And then there is sort of a discussion piece that goes along with it as well. So we've talked about content pedagogy and tooling, and let's finish things up by talking a little bit about openness and scalability. So all of the curriculum that I talked about is available at datasciencebox.org. In here, you'll see each of the learning units, slide decks for them, videos for them, the source code for the slide decks, and everything is openly licensed, so you can take it in full, or you can take bits and pieces of it and implement them in your classes. There is the sort of the GitHub repository that serves that web page, Data Science in a Box, and that's where you can find sort of all the source code for the curriculum as well. And there's an R package that goes along with it too, that has the data sets used in the curriculum, as well as the tutorials, these interactive tutorials that are distributed within this package. So the audience for Data Science in a Box could be anyone who's been teaching with R for a while but wants to update their teaching materials, or someone who's new to teaching with R and wants to build up their course, or maybe they came across just a slide deck somewhere on like Twitter or something, but they have no idea what type of course it belongs to. So this gives you a sense of sort of the full curriculum, even if you might borrow one or two things from it. We also have a community of educators that use Data Science in a Box. Some of them will actually contribute back to it as well, which has been lovely to see. And we have a Slack channel that you can join, and you can ask questions and, discuss sort of ideas around working with this curriculum. And if you're looking for an example of this curriculum implemented for a semester class, I taught this course for the last year in fall 2022, and you can take a look at the course website there as well. You see a lot of redundant materials, but it might be nice to see it sort of placed into a 15-week semester structure. All right, I'm gonna skip over that. And if you're sort of interested in scholarship around, sort of the full philosophy of this curriculum, back in 2021, I worked with a paper called A Fresh Look at Introductory Data Science with my then postdoc, Tori Ellison. And that's sort of a longer version of what you heard today in terms of the course philosophy, both in terms of the content and also the tooling and pedagogy of it as well. So thank you so much for listening. You can find the slides at bit.ly/dsbox-evolving, and the slides will then get you to all the other links that I've mentioned throughout the talk as well. And I would be happy to answer any questions.
Thank you very much, Minnie, for the wonderful class. In fact, we are having some questions already, and I think some of them you already told, but is very nice to ask again. Let me see. Diana asked, at which stage they start to engaging with data science? They start to create data visualization. And some people are discussing about the web scraping. First, get again.
Yeah, so students create their first data visualization literally in the first 10 minutes of the course, as I mentioned. Now, that's sort of, in a way, maybe you wouldn't call that creating your data visualization, because I've really given them all the code and all they've done is like sort of altered one thing. But what happens is by about week 5 of the course, they learn enough to recreate that visualization from scratch. And we actually come back to it on week 5 or 6 of the course after we've gone through units on data visualization and data wrangling, and say, look, that first visualization you saw, you can now understand all of the code that went into it. And all throughout the course, they continue to make data visualizations. You've seen each one of their final projects included some visualizations as well.
In some sense, I could find many similarities with the Hadley Wickham's book, isn't it? It's like
Mm-hmm.
So there's a lot of stuff that we are probably struggling with. Is the way you implemented the web scraping and the. I think most of us used to think this is a professor's responsibility to give proper data, but I realize you don't really need to do that. You let it kind of free, isn't it, or not?
Yeah, for the project, I don't give them a data set. So for everything else in the class,
You
the
have.
in-class examples, homework assignments, labs, yes, we give them data sets at various stages of cleanliness. So some of them are very sort of perfect data sets we start with, but then throughout the semester, we give them data sets where they first need to clean the data before they can, model it or visualize it. But for the project, they choose their own data. They do sometimes find it difficult to find good data. If a team is genuinely struggling landing on a data set, I will direct them to the Tidy Tuesday project and say, why don't you pick a data set from there? Because each one of those data sets is a CSV file. And, there's been now that project has been running for 3 years. Each week as a new data set, chances are a team can find one thing of interest to them. But it's really when students go out on their own and find something like this League of Legends game, for example, where they said, you know, I'm interested in this thing outside of this class. So I want to bring that thing I'm interested in and use the tools I learned in this class to analyze it. And I think that's where the really exciting learning happens. And it does mean that sometimes we, as the instructors or the TAs, need to help them get that data set in shape. And that's why when I said I think these open-ended projects are wonderful, but they do need course support, when you tell students find your own data set, you need to be able to help them in office hours if they found something but aren't quite sure exactly how to get it.
Okay. And Thales also asked something like about the environment. We were at first, we are starting an undergrad course next year, and we
Mm-hmm.
were discussing a lot on how to set up the environment for the students. But you are saying you at first mostly give the stuff in web applications, then web repositories and web browser to use R, etc. And R. So I think this is a very different setup for us. And then how did you implement that?
So there are two aspects to sort of the compute environment for the students. One of them is, well, the compute environments are in our studio, and we use a server-based solution. So again, either something like Posit Cloud, where you as the instructor don't need to set up anything, like the company Posit sort of sets it up for you. And then you get a subscription to it, or your students get a subscription to it, and then you can use that. And there, what you can do is you can install packages for your students. In fact, decide on an R version and stuff like that as well. And then you invite the students to your workspace there. And every project they create in it has all the packages you want installed. And you can also place data sets and whatnot in there as well. So you can sort of like prepare these projects for them, and they just come and make a copy of it. Alternatively, if you want to sort of brew up your own server in-house, like at your institution, our studio server, the piece of software that would allow you to run RStudio in the browser, is freely available for teaching purposes. What you need to then bring in is IT expertise for setting it up, like setting up authentication for your students and whatnot, and also either hardware or, sort of like virtual compute credits or something to run the compute on. Many universities are well set up to do this and tend to offer solutions like this for research purposes. So what we're saying is that we want to use those for teaching purposes as well. And then, so that's one aspect of it. And then the other aspect is every single assignment starts as a GitHub repository that the instructor sort of creates. And in that repository, there's starter documents like a Quarto document that, is a template that the students can use, any data files that they're going to use. So students go to GitHub, grab the URL of that repository that was created individually for them, and then clone that repository into the virtual compute environment that you've set up for them. So they are using RStudio. What they're not having to do is install R in RStudio, which is not that hard, but also install things like maybe tech, which can be challenging if they're going to render to PDF, or installing Git and GitHub and getting it working on your computer, is not trivial necessarily. So we get to overcome all these sort of difficult things that the students might need to do by doing it ahead of time for them.
Nice. We have two questions about Python and R, comparisons of using Python and R. As for some students in basic course on data analysis, they think that Python is the solution, not R or something. So both Nakamura and Fortunato, two professors asking about that.
So, I mean, I think in this day and age, it makes sense for students to learn both. That's the reality. I think, though, learning both in a semester in a single course is not necessarily the way to go. I think that would be a really challenging thing to do for somebody. Quite a few folks still use R for a variety of things, statistical modeling and data visualization being at the top of that list. I think the tidyverse tooling in R for introducing students to ideas of data science and sort of like understanding and wrangling data and visualizing it, honestly, is a lot more elegant than similar solutions in Python. So I think that R is a great way to introduce students to these. And then I would say throughout their, 4 years or so in undergraduate, they should totally learn both of these languages. Like there's no reason why they should only be focusing on one and not the other. But there's also no reason to completely omit one of these things, because it's an incredible tool for both like using as part of their work after they graduate, but also as a tool to learn with as well.
Nice. And just my curiosity of mine, do you also dive into that more like technical graph syntax, or this kind of modeling from graph syntax and this kind of new ideas that are brought in that book? New ideas for me, at least.
Yeah, we do a little bit of that. So we follow the R for Data Science book. We don't cover all of it because there's actually a lot more on sort of working with so in the second edition of the book, we have things around working with bigger data sets, working with databases. These are all important things. It just, something has to give. So we don't cover all of it. Instead, we do a bit more on modeling than some of the advanced programming that's in that book. But yeah, we follow it pretty closely, at least the first two sections of it.
Well, very nice. I don't think we have much more questions. People are trying to digest a bit because we are trying to, well, even then we have 10 students in the next year. Well, supposedly we will have 10 students just to start. So we'll have much more professors trying to adapt than students trying to adapt to our methods. So, Isabella just have another question. In course talk to non-statisticians, there may be classes with high heterogeneity in relation to different backgrounds and computational skills. Have you ever faced this type of situation?
Yeah, totally. I mean, this course is designed for folks with no background in statistics or computing. But even when I say that, some students come with some computing experience. in their high school, they may have seen a little bit of programming, probably not R, but they may have seen something. So there's definitely heterogeneity. One of the things we do is the teamwork that I mentioned. We set up the team, so the instructional team sets up the teams, not the students themselves. So I do a survey and I find out if students have computational experience, and we try to distribute that across teams, so each team gets one such student. So that's one way of sort of um, uh, addressing this. And another thing is, because once you have that survey data, you can look back at the student grades at the end of the semester. And by the end of the semester, there isn't a substantial difference between the grades of students who came in with some experience and who didn't. And that's another thing I try to communicate to students, because in the first few weeks, it feels like some students are a lot less scared of computing than others, and it can be intimidating for the students who are a bit more scared, but it gives them a nice assurance that by the end of the semester, you end up, there isn't a difference between them.
Nice. You do an incomplete block design for students' abilities.
Yeah.
So nice. I don't know how to proceed now, Geraldo. Isabella? I don't know how much time we still have. Tá fechado o microfone, Geraldo.
Extrapolamos 5 minutos. Pode concluir.
Tá. So we are on time. We're not, and probably people would like to ask you more questions. I will invite people to write directly to Minnie. That was so nice giving this presentation for us, and I hope Isabella will go to meet you in some time next year, or 2024, or 2025. I don't remember.
Yeah.
So, and I hope we will get in touch to you and use from your experience longer than that, or from now on. And thank you very much, Minnie, for the wonderful talk.
Wonderful. Bye.
Falou, pessoal. Era isso. Agradecer demais a professora Minnie.